Have you heard that the evil fossil fuel industry lied to us about climate change? Ever since the 1960s, they knew what had happened. It's all their fault, these bad people. They should just have told us that carbon dioxide causes global warming, as we all learned in school. Then we'd never have bought their oil. Oh, come on, of course we would have bought it. They could have renamed petroleum to planet-wrecking juice and put that in big red letters on gas stations, and we'd still have bought it. And what did you expect the fossil fuel industry to do? Refusing to sell us oil? They'd have gone bankrupt, and then someone else would have done it. Imagine John at the board meeting saying, "I think we should save the planet by destroying our company." Does that sound like a plausible event? Yes, the fossil fuel industry did some nasty things. There's plenty of evidence that Exxon paid people and poured money into adverts to exaggerate the uncertainty about climate science and to suggest that global warming might be beneficial. They did this until at least 2004, and we still see the consequences of this among climate change deniers today, when they dutifully regurgitate what Exxon fed them so plentifully. Other fossil fuel companies, including Chevron and BP, broadly financed lobbying groups that worked against laws that could endanger their business. Their communication was usually very one-sided. Please don't tell me that this surprises you. There's no doubt that the fossil fuel industry tried very hard to sell their product. But how much do you think they could possibly have known about climate change in the 1970s if scientists themselves didn't know much? It's not like climate models were a big secret only known to the fossil fuel industry. Exxon was understandably interested in the consequences of carbon dioxide emissions from fossil fuels when scientists first started to discuss global warming. They developed their own climate models and arrived at pretty much the same conclusions as the scientists. The Exxon predictions were really correct. Here is a quote from a 1979 Exxon memo which says, "Noticeable temperature changes would occur around 2010 as the carbon dioxide concentration reaches 400 parts per million. We actually reached 400 parts per million in 2013, and indeed around that time the temperature changes had become so noticeable that the science had definitely settled." Some physicists might now smugly say, "Of course they were correct, because it's just physics." I'd never ever say what I just said, because unfortunately a lot of people mistrust physicists and their models. I can't think of a reason why. And in the 1970s there was no data to back up this trend which the models predicted, so of course everyone distrusted the models. We know today that the predictions of the models were spot on, but they couldn't have known that. This Exxon memo from 1979 has received a lot of attention for how accurate the predictions were, and that has generated a lot of upset headlines claiming that they knew. But the memo also says, "It must be realized that there is a great uncertainty in the existing climatic models because of a poor understanding of the atmospheric, terrestric, oceanic carbon dioxide balance." And that was entirely right in 1979. It was still right in the 1990s. Here is, for example, what the climate scientist Michael Mann writes about his supervisor Barry Sussman. Barry was a skeptic in the true and honest sense of the word. He was unconvinced in the early 1990s that we could establish the human impact on our climate. This was a tenable position then, given that the climate models being used were still quite crude and that the warming signal in the roughly 1 century old global temperature data was only perhaps just beginning to peek out from the background noise of natural variability. The first IPCC report report from 1990 says likewise very carefully, the observed increase could be largely due to this natural variability. Alternatively, this variability and other man-made factors could have offset a still larger human-induced greenhouse warming. This skepticism about the model's predictions ceased to be a tenable position at some point as the data became better, but it wasn't like there was one particular day when that happened. You also have to remember that in the 1970s and long afterwards, everyone thought that oil production would peak around the year 2000. The real kicker didn't come until 2008, when oil production in the United States made this remarkable turn thanks to shale oil and fracking. In case you haven't kept track, the USA is now the biggest oil producer in the world. Even the fossil fuel industry couldn't have seen that coming in the 1970s. By blaming the fossil fuel industry for our lack of action on climate change, we're misattributing the mistake, and we can't learn from our mistakes if we don't identify them correctly. The mistake was not to think that the science wasn't settled, because it really wasn't. The mistake was first to not act despite the uncertainty, and second to not update our plans swiftly when new evidence came in. Too little, too late. And we're still making the same mistake. So keep on dusting those solar panels and maybe check out the new beachfront properties in the Alps. I recently saw a couple of headlines saying that a group of microbiologists discovered a protein that spontaneously folds into a fractal. I'll admit that I was a bit jealous, because we don't get pretty stuff like this in physics. Except, I just learned last week, we do. Look at this! That's a spontaneously formed fractal made of single atoms. And it doesn't just look nice. This could become the basis of a new type of quantum computing at room temperature. Let's have a look. The shape that you just saw in this protein and atom layer is known as the Sierpinski triangle. You get that by taking a triangle, dividing it into 4 smaller triangles and chucking out the middle one. Then you repeat this for the 3 triangles you didn't throw out, and repeat and repeat. Technically, you'd have to repeat this infinitely many times to get a true fractal. In nature, a fractal never has infinitely many repetitions. They have the largest and smallest scale, and in between you have this self-similarity. It's just like asking your kids to clean their room feels like an infinite repetition, but eventually the heat death of the universe will take care of it. Let's then have a look at those atomic fractals. What you see here are images taken by a scanning electron microscope. They created these fractals by depositing bismuth atoms on the surface of indium antimonide with a specific crystal structure. The bismuth then spontaneously forms these fractals. It's amazing, really. This assembly seems to be driven by spin-orbit couplings and triggered by the underlying crystal lattice, but they don't know exactly how it comes about. Actually, this isn't new. It turns out a group of Chinese physicists found this already in 2017. I just hadn't heard of it. Or maybe I did, but I forgot. Don't blame me too much, please. I've probably forgotten more than you've ever known. Won't be long and I'm fit to run for president. What's new is that another group now measured the properties of these microfractals, and they confirmed that they're topological insulators. Topological insulators won the Physics Nobel Prize in 2016. They're materials which are insulators in the bulk but conduct at the surface. They're not superconductors, but they have very stable ground states, and those can have quantum properties. That makes them interesting for electronic applications, especially quantum computing. But the issue is that so far topological insulators have all required either a high magnetic field or extremely low temperatures. It's basically the same problem as with superconductors. Interesting in principle, but in practice you only get them under extreme conditions, which makes them difficult and expensive to use. In the new paper, they now demonstrate that these atomic fractals are topological insulators that conduct only at the edges, and that they do this at room temperature without a magnetic field. This is extremely interesting because that means that if you put a current on the edges of these things, then that creates a basically noiseless quantum state, which you can then use for quantum computing. More specifically, you would use it for topological quantum computing. If you remember, that's the thing that Microsoft tried to get running, then had a paper retracted, and then Google came out of the blue saying they could do it better. The big deal about topological quantum computing is that topological quantum states are much, much easier to protect from noise. But so far, the topological qubits were all still cooled down to just above zero. So these tiny atomic fractals could be what makes topological quantum computing work. As you probably know, fractals are characterized by a dimension that's not an integer. So what's the dimension of those atomic fractals? The idea to give fractals a dimension comes from the following. If you take a line of length 1 and you scale that up by a factor 2, how much line do you have? Well, twice as much. If you take a square of area 1 and you scale that up by a factor 2, you have 4 times as much. If you take a cube, the volume increases by a factor 8. Generally, you can calculate the dimension of these shapes by asking, if you increase the scale, how much does the shape change? You measure the growth in units that we can call n, the factor f, and the dimension d, that is what we put into the exponent. So n equals f to the dth power. For our example, the factor f was 2. For the line, n was also 2. So for the line, we have d equals 1. For the square, n was 4, so d equals 2. And for the cube, d equals 3, as you expect. For a fractal now, you count the growth per iteration. For the Sierpinski triangle, for example, if you decrease the size of the triangle by a factor 2, then the area increases by a factor 3. Not as you would expect 4. So we have 2 to the d equals 3, or d is the logarithm of 3 divided by the logarithm of 2, which gives the dimension of approximately 1.58. What all of this means is that the future of quantum computing might lie in the 1.58th dimension, or maybe not. But then at least it'll give physicists something to brag about at parties. The German government, as you've probably heard, has phased out nuclear power. But did you know what their further plans are? They want to power Germany with, drums please, hydrogen. Yes, you heard that right, hydrogen. It's not just Germany which has big hydrogen plans. The United States also recently put forward a national hydrogen roadmap. The UK has one and the EU too. And I feel like it's about time I stop trying to be nice about it and just tell you how completely idiotic this is. Hydrogen has received a lot of attention in recent decades as a clean miracle fuel. If you combine it with atmospheric oxygen, that creates water plus energy. Totally carbon-free energy. It sounds good at first, but hydrogen has a bunch of problems. It needs to be kept. It quickly degrades materials it comes in contact with. It's highly volatile, meaning it evaporates and leaks, and if it does, it's highly explosive, and so on. I've talked about these issues in a previous video. Today I want to focus on a much more basic problem, that's how inefficient it is. The major reason that hydrogen has attracted attention is that it could be used as energy storage. It could take care of the problem that comes with wind and solar power, which is that the power generation fluctuates wildly on a daily, weekly and seasonal basis. The long-term fluctuations is where hydrogen is supposed to help. The idea is that you generate hydrogen from the excess electricity, put the hydrogen in a tank, and then generate energy from it when you need it and where you need it. The problem with this is basic physics. You see, we never create energy, we just convert one type of energy into another. Fossil fuels, for example, contain energy in chemical bonds, and we can burn that to create mechanical energy or electrical energy and so on. But every time you convert one type of energy into another, you lose some of the energy. So if you first generate electricity, then hydrogen from it, and then you use the hydrogen to generate electricity, electricity again, then the efficiency goes down to something like 30%. I've seen some people claim it could be 40%, but I don't believe that for a second. That means any electricity generated from hydrogen could have been 3 times as much if you'd used it directly. Consequently, electricity from hydrogen is going to be expensive. And if it's supposed to be produced from solar and wind, then you'll also need 3 times as much space. While electricity demand is increasing because we're all supposed to drive electric. Even without looking at exact numbers, this already tells you that for this idea to work, we'd need a lot of hydrogen very quickly and with lots of subsidies. Nevertheless, the USA and the UK have great hydrogen strategies and test facilities for clean hydrogen production. The European Union has a communication that sets out a vision for a roadmap to create a framework for an alliance that'll develop an agenda. I'm not sure just exactly what this means, but it's why the Brits left the EU. The issue with all these strategies is that they're 99% words. You see this nicely summarized in this figure from the International Energy Agency. On the left, you see the installed capacity to generate hydrogen from renewable energy using electrolysis by 2023. On the right are the plans for 2030. Why do they not put them into the same graph, you may wonder? It's because the scales on the vertical axis are so different. If you put them together, then the existing capacity would be about the width of this line. We're supposed to scale up by a factor 200 or so within 6 years. That should already make you highly skeptical of the feasibility, but the real kicker is this. Of the plans for this, only about 3% have secured funding. Clearly, investors are a little hesitant. And that's for good reasons, because the only way for hydrogen to be profitable is with huge governmental subsidies, which are going to become unpopular very quickly. None of what I just told you is a big secret. So why are some countries, like in particular Germany, going for this hydrogen craze anyway? There are 2 possible answers. One is they're just stupid. That's a possibility that we shouldn't entirely disregard, but I think the more plausible explanation is that it's really procrastination. It's a way to continue using fossil fuels. You see, natural gas is mostly methane, and methane is CH4, so that's a lot of H's. This is why it isn't difficult to build a power plant that'll run both on hydrogen and gas. This is indeed what the German government is planning. Yes, that's right. They're building new gas plants and call them green because they can, in principle, run on hydrogen. But in practice, the hydrogen isn't there and will never be there in appreciable amounts because it just makes no economic sense. The obvious outcome is that they'll just continue to run on gas. That doesn't mean that producing hydrogen from renewables is completely insane. It makes sense, most importantly, because hydrogen is widely used in the industry at the moment. Most of it is produced from methane, and the production releases carbon dioxide. It makes sense to replace this industrial hydrogen with hydrogen produced from renewables. But the hydrogen economy is basically an expensive way to apologize for the continued use of fossil fuels. While I was doing research for this video, I came across a quote from Elon Musk on hydrogen. He called it the most dumb thing I could possibly imagine for energy storage. Hello. Hi, Elon. No, you shouldn't run for president. Because Musk tweeted late at night and caused a nuclear war is not how I want to die. Love you too. This video was supposed to be about a refutation of macroscopic realism. At least that's what the press release said. It seemed interesting because I don't know about you, but to me the macroscopic world seems pretty real, most of the time anyway. But it turned out that what they mean by macroscopic is a neutron. Yes, a neutron, a particle so small you can't even see it in a microscope. and the only thing they did with it was to show that it has quantum properties. Why does this stuff get published? I decided to not make a video about this, but this reminded me of a quantum puzzle that tripped me up, and I thought you might want to try your hands on it. And then I'll explain how this is related to the macroscopic reality thing. First thing you need to know is that quantum particles are not point-like. They're probability distributions that you can think of like clouds. The higher the density of the cloud, the more likely you are to find the particle there. The second thing you need to know is Heisenberg's uncertainty principle. The better you know where a particle is, the less you know where it's going. This means that the probability cloud of a particle will generally run apart if you don't look at it. Say you put a quantum particle in the middle of a box, then you stop looking at it. You knew where the particle was, so you don't know which direction it moves, so the probability distribution will spread. When you later make a measurement, you have a chance to find the particle outside the region where you knew it previously was. And once you measure it, you know again where it is, so the probability distribution contracts. So far, so unremarkable. The third thing you need to know is that there's something that's called an interaction-free measurement. You do this by exclusion. Say you measure only one side of the box and do not find the particle there. Then you know it's on the other side, even though you didn't touch the particle. You can do this, for example, by shining light onto one side of the box. Then you measure whether any of the light changed direction. If it did, well, you know the particle's there. If it didn't, you know it's on the other side. The fourth thing you need to know is that momentum is always conserved, and that's also the case in quantum mechanics. Momentum is the product of velocity and mass. This means that if the mass of the quantum particle stays the same, the particle can't change direction unless you interact with it, in which case it might get a kick. So we have A, quantum particles are probability clouds. B, those clouds spread if you don't measure the particle. C, you can measure part of the probability clouds without interacting with the particle by excluding some regions. And D, a quantum particle can't change direction on its own. That said, here's the thing that tripped me up. Suppose I put a particle into the middle of the box. I wait for a bit, then I measure it on the right side. The particle isn't there. I wait, then I measure it on the left. The particle isn't there again. Then I measure it right, and again the particle isn't there. Quantum mechanics says that this can happen. It's not very likely, but it can happen. Indeed, this was the idea of a paper I talked about a few months ago. I'll say a little bit more about this later. The issue is now, if you do this sequence of measurements, you know that the particle must have gone in a zigzag from left to right. It changed direction, so it must have changed momentum. But you didn't interact with the particle because the measurement was interaction-free. How does this not violate momentum conservation? Something's clearly wrong, but what? Pause the video here if you want to think about it, because I am about to explain it. It's indeed true that if you chop off a wave function at a sharp boundary, the remainder will spill over into the other side. It's also not that quantum mechanics can magically violate momentum conservation, or that there is some fluff going on about interpreting probabilities. No, it's that this supposedly interaction-free measurement can't have been interaction-free. Let's look again at how this works. You shine light on one part of the box and see whether it comes back undisturbed or gets scattered. If the light doesn't change direction, you know nothing was there. Sounds plausible. But to know that the light doesn't change direction, you need to know which direction it was going in the first place. You need to know the momentum of the light. And if you know the momentum of the light precisely, you don't know where it is. So you can't know that it was only on the one side. And the other way around, if you know for sure that the light was only on one side of the box, you can't know exactly what its momentum was, so you can't tell that it didn't interact with the particle. That is, this zigzag which the quantum particle makes, that comes from the measurement. It was not interaction-free. I'm pretty sure that's correct because after digging around in the literature for a week or so, I found out that someone had actually discussed exactly this problem already in 1981. I'll leave you a link in the info below. The reason I was thinking about this is that I made a video a few months ago in which a group of physicists proposed to use this kind of interaction-free measurement to demonstrate that macroscopic objects do make quantum jumps. If they were able to actually show this, that'd be a really big deal, because this would mean that quantum effects survive for large things. This is what physicists call a violation of macroscopic realism. But I'm now pretty convinced that this paper is just wrong, because the measurement isn't interaction-free. I could now go and write a comment and submit it to the journal, but I thought we'd have more fun with it on YouTube. Did you figure it out? Let me know in the comments. Have you noticed that I don't talk about new battery technologies anymore? It's not because there's nothing happening. There's like 24 press releases each week. They're all great breakthroughs. Then you never hear of them again. That's why I stopped talking about it. But just the other day, I came across a study about the hype cycle of battery technology, and that really helped me put things into context. Let's have a look. The hype cycle is not just a word. It's a semi-scientific technology assessment tool that was introduced by the American IT firm Gartner in 1995. The idea is to look at how much attention a technology attracts, the visibility as a function of time. The early visibility of a technology is driven by excitement that'll fade away unless the technology is sufficiently mature to make it into application. The hype cycle then combines both the initial excitement and the maturation. It has 5 distinct phases. There's the initial trigger, the peak of excitement, the trough of disillusionment, the slope of enlightenment, and the plateau of productivity. Sounds like my journey through New Year's resolutions. Peak excitement in January, trough of disillusionment by February, and if I'm lucky, a plateau of productivity by December. A technology can see several peaks of excitement before it matures. Artificial intelligence, for example, just passed its 4th peak of excitement and made it into productivity with only little disillusionment, mostly concerning the number of fingers on a hand. Nuclear fusion has also seen at least 2 peaks of excitement previously. After the initial one, there was the cold fusion enthusiasm in the 1990s. The 3rd fusion hype cycle hasn't yet peaked because it'll take a few more years to see whether any of the new fusion startups deliver. I hope we'll finally make it to productivity. Okay, so this is how the hype cycle works. Now, what about those batteries? Battery technology is getting more important by the day because we're all supposed to drive electric and we need them to store renewable energy from intermittent sources. The most widely used batteries at the moment are lithium-ion batteries. Their major problem is that they're quite heavy, or to be more precise, they don't store as much energy per mass as, say, fossil fuels. They have, as we say, a lower energy density. So one of the major things we want from new batteries is a higher energy density. But this isn't the only thing we want, because besides energy density, we also want them to be able to deliver energy quickly. That's the power density. We want them to reliably recharge thousands of times. They should be environmentally friendly, robust and durable, safe, and last but not least, cheap. That's a long list, and that's why you see so many battery headlines that then vanish in the junkyard of science news, because you might have found a way to improve one thing and then you fail on another. It's like looking for a unicorn that can also do your taxes. To make the battery hype even more confusing, scientists aren't just on the lookout for new compounds, but also for new technologies or new methods of manufacturing. This is why battery technology is a mixed bag. that contains everything from sodium-ion batteries to silicon anodes, solid-state batteries, to production methods like high-speed stacking, though that sounds like World League Jenga to me. In the new paper now, they have classified all those batteries according to their potential and the expected time to market. This is their summary. You can see that they think we have several transformative technologies coming up in the next couple of years. First, there are silicon anodes for lithium-ion batteries. Some estimates say that they could increase energy density by up to 50% over the currently used graphite anodes. Then we have 2 improvements to the manufacturing process that should bring down battery prices. Then in 5 years or so, we might finally see solid-state batteries, and then there are sodium-lithium and lithium-air batteries maybe in 10 years from now. They also put these technologies on the hype cycle, which looks like this. To understand this graph, you have to read the horizontal axis as the time past invention for each item and not a year. For example, they say that sodium-ion batteries are at peak excitement, but they yet have to go through the trough of disillusionment before hitting the consumer market. Solid-state batteries are currently in the valley of disillusionment because so much's been talked about them and yet they haven't become reality. You could see this disillusionment clearly in a recent announcement from the Japanese company TDK that said they'd made a big breakthrough with solid-state batteries and everyone was like, sure, whatever. But those will come eventually. And we also have a couple of improvements that are basically ready to go, though none of those were in the transformative category. It could be, of course, that those people are just wrong. However, they made some effort and I think they know what they're talking about, or at least more than I do. Then again, who knows? Maybe in 5 years we'll all have cars with nuclear fusion reactors. Thanks for watching. See you tomorrow.